All right. I'm not sure about how y'all are doing, because only about 2 or 3 of you asked questions. But that was this week. Starting 6-1 here. Theoretically, 6-2, 6-3. I will likely do practice here over those 2 models. 6.4, quiz number, what would that be? 9, 10. 10. 6-5, 6-6. Probably some more practice over both. One, two, three, four, five. See, here's the deal. We got a couple of days to play with. We're going to be a couple of days ahead of schedule. So we might be able to get a double dose of some stuff if it's really monkeying with us. But something you need to be aware of. A, the test that we took on Monday, that is your quarter grade or your midterm grade. But B, I don't know what it's going to do, but it's going to do something. Forecasts have changed. Last night said that Tuesday, Wednesday, Spearfish would have a total of roughly 14 to 19 inches of snow. My wife texted me this morning and said current model is bumped up to 25. As of last night, Deadwood was supposed to have 27. So, but they get, if y'all know how geography works, topology, Spearfish is right at the northern end of the hills. So it all depends whether that air mass hits the hills and shifts around it, or hits the hills and pops over it. If it pops over it, it gonna puke on us. So the likelihood that we have a snow day, or even 2, next week, right now is pretty high. It all depends on what it's actually going to follow that forecast or not. Y'all remember that big whoop in October? Okay, I got hit with like, well, what did we have? Like 14 inches, and it was just heavy, like concrete. Cracked the casing on my plow. Okay, it was bad. I live outside of Bell, and they said we were going to have 2 inches. So the weather right at the north end of the hills here gets kind of weird. Just letting you know that right now, it looks like something big's coming next week. Okay? And if that happens, y'all, I don't do the whole snow day home lesson thing. That's dumb. You're at home. You're probably either just sitting there on Xbox having fun, or maybe you're looking after a younger sibling. Maybe dad tossed you a shovel and said, get to work. I don't know. Me, I'm clearing out snow for my entire neighborhood and looking after my kids. I ain't got time to do schoolwork. I assume that about half of you are in the same boat. So if that happens, it just shoves everything down a day or 2. Okay? So just letting you know about that. Otherwise, y'all got a new packet of notes. Should have picked it up when you came in. Here we go. I certainly hope you know how to use lines and linear equations, because that's kind of the entire basis of this chapter. If you can't line, then you can't do this chapter. Pure and simple. Because this is where we start to get into applications of those. You're going to see a lot more word problems this chapter. And this is how we normally end algebra half, but I said we're a little bit ahead of time. We can either do extra review before our final, or maybe sprinkle in some new stuff that you would need for next year, like exponents. I don't know. I kind of want to talk to Jameson and see where he wants y'all for Algebra 1. Y'all know, like, for after this class, y'all take Algebra 1. You can either do it year-long, every other day, like this, or you can double up. It's only freshmen that have to do an every other day math class. Starting next year, you could do Algebra 1 and Geometry, but it would be every day 90 minutes. Every day 90 minutes. And that's how the rest of our upper classes are. But currently our Algebra 1 would be Jameson. I think Spear has one section. I want to say McCreary has 2 sections. Okay, so I need to talk to them and find out where they want you to be for Algebra 1. Whether I should squeak in some exponent stuff or just go back and make real sure that we know all this. Here we go. Those look an awful lot like rates. What have we talked about in the last 2 chapters, the last two and a half months? Do you remember what we do with rates? Okay, rates and ratios. I'm going to compare them. What do we think? Will they pass them or not? How long do they have to pass them? What could you do? Could you guess and check? Could you make a table? Can you write an equation? See, we wrote out a couple of different models, a couple of different ways to write equations last chapter, and I hope you remember them. You remember how this looks in words? Wrote it down a few times. We wrote it down back in chapter 4. No. Words. Rate x plus start, okay? If we had point slope form, y minus remember that one. We didn't use that one as much, but boy, when you have it, it comes in real handy. No one's got their chapter 5 notes to look it up. Okay, we're going to be using these a lot. Okay, we still have slope and it's still rate. But we always had a coordinate with it. Coordinates are x1, y1. Input, output, x, y, in, out. So that's exactly what I would write. I have some sort of input and some sort of output. Those ones are usually something like Spearfish High School is growing by about 20 students per year. That'd be a rate. In 2018, we had 680 students. That would be an input-output. This year, that many students. I want to say, thanks to your class, when they say we're like 802 or something.
Yeah. Like,
it was like right around 800.
Yeah, that's the reason why teachers keep moving up.
Yeah. So yeah, your class is pretty big. There's a pretty big bottleneck between you and the next like 3 classes. And then after that, right now, it looks like it'll settle down. But who knows? A lot of folks moving here. Then we did standard form. Standard form was ax plus by equals c. And we'll actually use that one. We're going to use these two quite a bit in this chapter. Because this one would be a lot more, shall we say, word friendly, where they give me a rate for one thing, so I'll say rate 1, a rate for a different thing, and then a total. Think about how many of you get that gift card from grandma who doesn't know what to get you for Christmas, okay? Maybe it's 20 bucks, maybe grandma's loaded and gives you 100 bucks, I don't know. But you get that gift card, and I'm gonna go buy things. Well, what happens if I wanna buy, say it's Best Buy gift card. I go to Best Buy and I can buy games and I can buy Blu-ray. Well, say these are 40 a piece and these are 20 a piece. I have 100 bucks. That's an equation right there. 40 per game, rate. 20 per Blu-ray, rate, equals 100. My total. Okay? So we're going to see these an awful lot in this chapter. I'm asking, with our downhill skiers here, what kind of information are they giving us? Are they giving us rates, totals, starting amounts, input, output? What? They definitely gave us a rate of weight each skier. So that means 2 different equations. Rate of skier number 1, 100 feet, times however many seconds we're going. Rate of skier number 2, 110 feet per second, times however many seconds I'm going. And it says skier 1 starts 5 seconds before. 5 seconds before. So if he's going 100 feet per second and he started 5 seconds before, I would add the 500 feet that he is ahead. Right? He went for 5 seconds. He was going 100 meters or 100 feet per second. So he's 500 feet down the hill before skier number 2 starts, but he's going faster. Will he catch him? Okay. Well, I could do that by a table. Could say skier number 1, skier number 2. And we'll just keep going in iteration of how many seconds. Well, at 0 seconds, this dude's at 500 feet down the track. This guy's just starting. At 1 second, this guy's at 600 feet. This guy's at 110. This guy's at 700 feet. This guy's at 120. So he's got the head start on him. The question is, when we get all the way down to 5,000, will he pass him? Yeah?
220.
220? What? Oh! I've had a thumping headache since like 5 a.m. You rack it in today. Okay? You are getting there. 10 out of 15. Don't wait until May. It's going to keep doing that all the way down to 5,000. So there's this idea, and this is what we're going to do throughout this chapter, that if y is this stuff, I can replace y with that stuff. And I just turn myself into an equation with one variable. Okay, that method is called substitution. If I subtract this stuff, it's called elimination. Or, what if I have a graph, I think that's what today's all about, where I say this guy started already down the hill at this rate versus this guy started here, but he's faster. The question is, right here, is that before or after 5,000? And that's, what, 10, 5,000, 50 seconds. Will they pass? It's 5,000 feet long. It's going to take them 50 seconds. I don't think that's going to work. Okay. This idea that I can do two graphs at once is what brings me into what's called a system. Okay. A system is when I got more than one equation. And today's is actually super simple as long as you know how to graph a line. Okay. Do I know how to graph a line? Get a little bit of vocabulary up here. A system is when I have two or more equations. It's not uncommon that you will see the system with this little squiggly bracket in front of it. A little squiggle bracket says these two go together. They are the system. Anyone ever know a friend, or maybe you yourself are plural? No? Okay. Someone who is plural is someone who has various personality sets, and they work together as a cohesive system. Okay. Someone who has various personality sets who do not work well together, fighting for dominance, would be classified as having a multiple personality disorder. It's possible to have various personalities and they coexist. Okay, you actually look throughout history, there's a lot of really cool examples of people who have been just fine with that. This system, this group says these two things are going to go together. Well, graph both of them. Graph both of those right here. Y'all know how to graph a line. Not on two separate graphs. Put both of those on the first graph. Y equals mx plus b. Where do you start? What's your slope? Graph them both on the left graph. And we'll talk about what it means. Spent a month and a half on lines. All right. Remember, rise, run, x plus start. Okay, good old slope-intercept form. So equation 1. Where am I starting? 2? Oh, okay. Remember that it's a y-intercept. So either you say a y-intercept of 2, or you say 2 on the y-axis, or you say the coordinate 0, 2. Just be careful. And then, what's the slope if there's nothing in front of x? 1, right? There's a little invisible 1 there. And because it's positive, I know I go up and to the right. So from there, up 1 over 1, up 1 over 1, up 1 over 1, or I can back that math up and go the other direction. If this is up the stairs, fall down the stairs. Down one, left one, down one, left one, down one, left one, down one, left one, down one, left one. Connect the dots, and I implore you, use a straight edge and actual graph paper for this section. If you try to wing it on non-graph paper and just freehand the line, I'll tell you that these are not going to end up as nice as you want them, because accuracy really matters here. Okay, so I'd call that blue line. How about red line? Start at -2. Slope is 3. So it's +3 means go up, over 1 means right. So up 3, right 1. Up 3, right 1. Up 3, right 1. Or down 3, left 1. Here, I'll extend this guy out a little bit too.
Wait, isn't the red line supposed to be on the other graph?
No, I said do them on the same graph. We are talking about a system of equations, plural. See, the purpose of a system of equations is an equation can represent a constraint, an idea, where this is a relationship between input and output. Well, what happens when I want those two to meet? What happens when I want them to have one solution? Okay, this blue line is every single solution you could ever think of for this equation. Say, not all of them. Yeah, seriously. What if I put x as pi? Pi plus 2. Well, pi is 3.1415926 blah, 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 blah. Pi plus 2 then would be 5.14159, so 1, 2, 3, 4, 5 point, it's right there. Everything you can think of. The red line, every solution you could ever think of for the red equation. So what is this? Blue line is all the blue solutions. Red line is all the red solutions. What is green dot? It's an intersection. It's a solution that makes both of them true. The point 2, 4 is called the solution to the system. The solution to the system is the point that makes both equations true. Think about it this way. Blue line. My wife wants Mexican food. Like, she wants Mexican food. That she is dead set on. That's what we're having tonight. Red line. I hate Mexican food. I can't stand it. Where will both of these things be happy? Guadalajara's. They got the gringo menu on the back. I could still get the chicken sandwich and fries. Okay? It's the place where both of them are satisfied, where both of them are true. And I can prove it. Because if 2, 4 is really a solution, I should be able to take these two equations now and say y equals x plus 2. I should be able to say y equals 3x minus 2. And if I put the numbers 4, 2, 4, 2 in for y and x, both of these things should be true. And when it says use a graph and check your answers, that's exactly what they mean. You're going to graph the two lines, see where they cross. That's the magic place where they're both happy. That's your solution. That's your answer. Now plug it into both equations and show that it actually works. 2 plus 2 is 4. Yay, I win. 6 minus 2 is also 4. 4 equals 4. Yay, I win. I just showed that this coordinate makes both of these true. But I wasn't going to find that coordinate until I graphed them to see where they both cross. Okay? So, same thing. Graph this equation. Graph this equation. And tell me where the lines cross. Where the lines cross is your answer, your solution. It's the place that both equations are happy. When you get that coordinate, when you see where they're both true, both happy, plug that coordinate in for x and y in both of them to make sure that it really does. She wants Mexican food. I hate Mexican food. I think Guadalajara's is the answer. Well, what happens when it turns out they're out of their chicken sandwiches? I don't know. I don't know if I trust that plain quesadilla. You know, me and just pepper jack cheese don't get along. So maybe it wasn't the solution. I have to plug it in and I have to check. I got to make sure. Don't just graph one of them, graph both of them on the same grid, see where they cross. The more points you make, the better. Because odds are one of those points is going to be the answer. You really got to know your lines or this ain't going to work. You have to know how a slope works, how a y-intercept works. Okay, did we handle it right? It should not be long, not at all. First one, I start at 4 on the y-axis. 1, 2, 3, 4. I have a slope of 2 over 1. It's positive. Remember, 2 over 1, positive means up, always to the right. From here, I go up 2 and right 1. I can go a little off-road. Or better yet, how about down to left 1? Down to left 1, down to left 1, down to left 1, down to left 1. And I'll connect the dots. Go over to my other graph. I start at 2 on the y-axis. There's nothing in front of the x, I assume it to be a 1. There's a slope of 1. From here I go up 1 over 1, up 1 over 1, up 1 right 1, or back it up. Down 1 left 1, down 1 left 1, down 1 left 1, down 1 left 1, down 1 left 1. Connect the dots. And I see the magic combination. No, that's ugly green. There we go. I see that both of my lines ended up at negative 2, 0. Okay. Y'all probably know spearfish businesses better than me. Purple line, I want ice cream. Orange line, my wife wants cake. She likes cake. She's a big cake person. Where can I get ice cream and cake in town? I was thinking like sit down and eat something as a treat, but
Maybe.
all right, I guess we just go in the grocery store, pick them both up, and go home, huh?
Maybe Dairy Queen.
I suppose they got
You can buy like a
ice cream cakes, so if it's oh, okay. I thought one of those little downtown shops would, but guess not. Prove it. Show me that actually is the answer. I should be able to say that equation, y is 2x plus 4. That equation, y is x plus 2. I just said negative 2, 0 is my answer. I should be able to put 0, negative 2, 0, negative 2. Remember, the coordinate is x, y, but in the problem, it was y then x is how the equation was written. Just put x in the x spot, y in the y spot. And I get negative 4 plus 4 is 0. Negative 2 plus 2 is 0. It checks out. It worked in both. You really want to be careful about these because sometimes you graph this line right, but you graphed this line wrong. And you get where they land, and you go to plug that in, it turns out it wasn't the solution, but it works in one of the equations, not the other. Well, that's because it's a solution for the line you drew correctly. But since you didn't draw this line correctly, it won't work for that equation. It's also a nice way to know which line you goofed up. Okay. So it's a lot of words to say, a system of equations is more than one equation. You want to know what the solution to the system is? Graph them both and see where they cross. So, graph them both and see where they cross. Well, rut-row, Raggy, what happens when I don't even know what the equation is? You have to write it now. Okay, this is where all of that word stuff that I put up here at the beginning comes into play. So, you're going to study the weights, 2 alligators over a period of 12 months, initial weight, and the growth rate. Boy, what does that sound like? Initial weight and growth rate. Start and rate. It's y equals mx plus b. Okay, so initial weight. So that's my start, plus 4. Rate of growth, 1.5 pounds per month. Okay.
Will we sorry.
Yeah.
Sorry. Will we ever be like will we ever have to like find the slope on these? Or will it always give you just
Oh, yes.
okay. I'm just curious.
Not often. In algebra half, normally we give you the pieces that I talked about at the beginning. It's not often that we'll give you the 2. That's when you start getting systems of equations, like when we did our scatter plot. You know how we had our scatter plots and you'd pick your 2 points and make your equation from those? That's something you will review either next year in Algebra 1 or you'll expand upon in the beginning of Algebra 2 when you review this stuff, where you make line 1, they give you a different set of data, you make line 2, and you say, when will these two models meet? But that's a little more advanced past where we're at right now, so probably not. If they ever do, I'll give you a heads up. Oh, initial weight, 6. Rate of growth was 1, so 1x plus 6. I just need to graph these two. Over a period of 12 months. That's really telling in the graph space that I have. How far do I need to go out? 12, right? 1.5 per month. If that was a little confusing, maybe we should have done our very, very first step, our rule 0 conversation that says, I need to say what the crap my variables are. If I don't know what my variables are, I have no idea what's going on here. So, what is x? 1.5 per what? It's 1.5 pounds per what? Per month. So x is going to be my months. And when I take this many months of growth plus the 6 pounds I started with, it gives me their, which was what? Their weight, their total weight. Ew. How many of you write cursive? Like actually still write cursive? Only our signatures, right? You got that one teacher in elementary school who makes you write everything cursive, and after that, no one cares? Yeah. It's a dead medium. The reason that we learned cursive was because the ink in calligraphy pens and quills would splatter if you tried to print. But if you had it in one continuous stream, it wouldn't. Well, now we just type everything. Or have a mechanical pencil, or a sharpened pencil, or a pen. So it's literally only used for signatures now. Which, that's going to be dead soon too, because you'll just have biometrics. Use your thumbprint or your retinals or whatever. So I got my variables, I got my equations, I need to graph them, I need to go out to at least 2 months. So down here I'm going to say this is, 12 months. So I go by twos. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And then weight. They're both starting at 4 pounds and 6 pounds, and they're going up from there. What should I do? Go by twos again? Yeah. I should be able to fit everything. So don't just say weight in pounds. Tell me what unit. Because how many pounds something is versus how many kilos something is. Any of you ever hit the weight room? If you come belly up to the bench and say, go ahead, let's put 150 on there. Is that 150 pounds or 150 kilos? Those are different things. One of them you probably be fine with, maybe. I don't know. Some of you look like you got some buffness going on. 150 kilos on the other hand, now you're talking about almost 300 pounds. That's going to squish you like a bug. Okay? Now, do your graphs. Start at 4. Oh, we didn't finish it because we got distracted. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. All right, start at 4. Now, when you're already going by a scale of 2, this is going to be kind of annoying to go up 1.5 and over 1. If I'm going up 1.5 and right 1, how about I just double that and call it up 3, right 2? It's still the same ratio, right? It would divide or reduce down. So from here, I'll go up to 3 over 2. Up, 1, 2, 3 over 2. Up, 1, 2, 3 over 2. Up 3 over 2, up 3 over 2. And please use a straight edge. Okay. Do the same thing for red line. Well, if red line currently has a slope of 1, up 1, right 1, I can multiply that by whatever I want. So since I'm going by 2's, how about I go up 2, right 2? So we'll start at 6. Up 2, right 2, up 2, right 2. Check it out. Up 2, right 2, up 2, right 2, up 2, right 2, up 2, right 2, up 2, right 2. And if I make enough points, odds are one of the points that I made is going to be my answer. Because those two lines crossed at 4, 10. So when they answer the question, after how many months did they weigh the same amount? Well, I use my coordinate with the variables we wrote down at the beginning to say, after 4 months, both are going to be 10 pounds. Okay? I had to see where the two were crossing. I had to graph the two equations. Here, I'll get rid of the spiral. Been doing coterminal angles with pre-calc recently, so I'm used to just drawing spirals everywhere. Yeah, that was something we did in class yesterday. Yeah. So the graph off to the left there. Finn thought it was fun, so he decided to just keep making graphs. So I know that you can graph a line, or I know some of you can graph a line. Okay, we've got to buckle down, make sure we know what we're doing. Graph the lines, see where they cross. Graph the lines, see where they cross. Plug it in and make sure that it works. But sometimes, like in this problem, you are going to have to write the equations. None of this is going to work if you can't write the equations, which is why we spent so much time on it at the beginning of this semester. There you go. Satellite radio. How many of you got Sirius in your car? Okay. I'll tell you both of these are y equals mx plus b. What's the rate? What's the start? What's the rate? What's the start? Better yet, what's my x? What's my y? What are the, always start with your variables. What are the two things they're talking about? For every one of these, it does this. Is it for every Happy Meal, I pay this much? Is it for every week I'm a gym member, this is my fee? Okay, if you're struggling with how to start, X is the number of months you have the membership. Y is the cost. Because, remember, independent and dependent variables, my cost depends how many months I had it. Okay, they're both y equals mx plus b. What's my rate? What's my start?
Is this right? I'm confused. I'm guessing if I kept going, I'd cross somewhere, but.
They will cross somewhere, but because your rates are so close together,
Mm-hmm.
we're going to need to go out way more than just 10 months. Okay. We're going to need to go out way more than just 10 months. My rates are very close together, so it's going to take a while for these two to match up. No, it shouldn't be terrible. Right. See, x is 5. No. See yours again. I think that should land in the middle.
I erased it. You can kind of see it.
Okay.
These two, and then these two.
Sub 10 over 1, up 10 over 1, up 10 over 1. Oh, make this scale go bigger.
What?
The slope is 10 over 1. So you're going to wham, wham.
I think that's what I did. So start at 20. Like you go up 2 over 1. 2 over 1, and then you start at 15. You go up 11, and that's like right here, and then you go over 1, so like right here. Do you see that?
Maybe it's our y-axis that's too small. Maybe we need to condense this down because you said it right. Yeah. They're going to meet up here.
Oh, that's true.
Yup. Maybe it is within 10 months, but our y-axis wasn't big enough. Okay. Most of us got our equations by now. You got $10 per month, so that's a rate, plus an activation fee of $20. So whether you're there for 1 month or 12 or 38, You still got to pay the $20, so that's your starting amount. Rate for the second plan, we got 11x plus $15. Less of a fee, but more expensive per month. Now these will land together at within those 10 months. So I'm going to say months. Go 1, 2, 3. Cost. So I want you to think about what would be a reasonable scale here if, we'll start with blue because that's actually pretty easy. $20. After the first month, it's $30. After the second month, it's $40. 50, 60, 70, 80, 90, 100. What's a reasonable scale? Maybe 10s? I don't know if that'll fit my intersection or not. Maybe I'll have to go to 20s or 30s. But I'll start with 10s, and if I have to erase stuff, I have to erase stuff. Okay? It does fit? Okay. So I'll say 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. All right. This guy. I'm starting at 20, and I have a rate of 10, meaning a slope of 10. So up 10, right 1. Up 10, right 1. Up 10, right 1. That's nice and easy. Connect my dots. What is he doing in geography today? Because I've been hearing the music blasting all day long. Any of you have NIDA for? Oh, is that government? Okay. Been hearing that all day long. Next one, I'm going to start at 15. So be careful, I'm halfway through the box. Okay, now like Amy said, if it's up 11, it's going to be up a box and a little bit. Up a box and a little bit. If 11 over 1 is going to be problematic, what if I did times 5? Because I know where halfway through a box is because that's my 5s. Right? I could say up 55 over 5. Now, if that doesn't make any sense, I'll just try to eyeball the 11 over 1, and hopefully we'll see that it does work. So up 10, 11, and over 1. Up 10, 11, and over 1. Up 10, 11, over 1. Okay, so I should now be at 15 to 26, to 37, to 48, to 59, to 60. 70? Oh yeah, because we started down here. Wow. Okay, yeah, that's fair. That one's going up there. They're really close together, right? Well, couldn't I from here have gone up 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55 over 1, 2, 3, 4, 5. Okay, so I can eyeball the graph, or I can change my slope, Jesus fish style. I can change my slope to make it a little more reasonable. And those two lines, yeah. Oh God, that's atrocious. You get the idea, right? Use a straight edge. Okay? And I see that those two are going to cross. I swear they cross at 570. Don't just do that and quit. Read the problem again. One service is this. The other service is this. In what month was the cost the same? Answer the question. In what month was the cost the same? The 5th month. Okay? That's your answer. Now, when it comes time for homework, you know who you are. No, you did not do the problem. Okay? That is not doing the problem. You do not get credit for that. Do them for real. Get yourself graph paper. I got a stack of them up there, top right corner. You can always just Google printable graph paper. Just print it to wherever, snag a piece, and go. Or, instead of getting Pop-Tarts all the time, throw $1 in there and I got a whole stack of notebooks. Okay? So, when I graph these things, one of 3 things is going to happen. Option 1. I go to graph my 2 lines and they actually cross. If they cross, there is a solution. It's right there. So I would call this, down here, I call it consistent because it has a solution. I call them independent because it's one solution. Meaning they're independent of each other. The 2 lines are not the same thing. But sometimes when I go to graph my lines, maybe they're not both in slope-intercept form. Maybe they're all jumbled up. I go to rearrange my lines and they end up looking the same. In fact, when I go to graph them, I graph this line, and then I graph the other line and I say, wait a second, they're the same thing. In that case, it is consistent because it has a solution. But they're called dependent because they depend on each other. They landed right on top of each other. Pay attention up here, infinitely many solutions. That's what it's officially called, infinitely many solutions. Because remember, this line is every solution possible for the equation. It's a picture of every solution possible. And it goes forever. If it goes forever, there's an infinite number of solutions. Well, yeah, there's going to be an infinite number of things that make the equation true because it's the same equation. I can pick any x, I got a y that goes with it. That's one of my answers. Right above this, below it, wherever you need to write it, there's a big difference between infinitely many solutions and that is not all real numbers. Infinitely many solutions is not all real numbers. Because everything on that line is a solution. That line goes forever, there's an infinite number of them. But can I say that this point is a solution? Is this on the lines? Will this make the equation true? No. So since this won't make the equation true, it's not an answer. If I can find stuff that is not an answer, it isn't all the real numbers, it's just these ones. There's an infinite number of them, but it's not every number. Okay, I can't just randomly pick, negative 10, 0. No, that doesn't work. Kind of like, you've heard that phrase like, there's more than one right answer. Or they'll say, there's no one right answer. But there are wrong answers. How many times have we had the open-ended questions? And then if you ever look at the answers in the back of the book, it'll say something like student answers may vary. Yeah, there's more than one right answer, but that doesn't mean everything's an answer. I can't just put a number and it works. Okay? It's like asking Ralph for his credit card number and he says 7. Okay? It doesn't work. Sometimes, we ran across these last chapter, I go to graph the two lines, I want to see where they cross, it turns out they never will, because they're parallel. They will never cross. Train tracks. In fact, if you have train tracks that cross, you end up on the 5 o'clock news. Okay? Hasn't been such a big deal lately. Y'all probably too young to remember, but there was a stretch about 10 years ago where Amtrak was having problems. There was a train derailed somewhere in the country about every other month. If I remember right. I think there is one right now. Like, there was a lot of them. And about every month or two, you would see on the news, the helicopter flying over it and the cars piled everywhere. And it's because those tracks, well, one of them bowed or warped just enough that it came off the rails and the whole thing crashed and burned. In fact, Ava's not here today. I'm pretty sure her dad worked for Amtrak. I knew her brother when he was in Game Club. And I swear that their dad worked for Amtrak or Burlington Northern or something. And like that was the thing, was just, you're going to go to this hut and you are going to man this station. You are going to take care of this stuff. Make sure nothing crashes, which most of the time meant stare at a computer screen. And then play Magic, which is where Brandon got all of his cards from. His dad's sitting there bored. So those tracks will never meet. So if I ask you, where will they meet? And you say, no. What's the answer? There isn't. There is no solution. That would be, my wife wants Greek food. I want ice cream. Where in Spearfish are we going to get Greek food and ice cream? Nowhere. There is no solution. There is nowhere that makes this happy. Okay? I want lasagna and a steak. Where is that happening? Actually, you might be able to do that at Perkins. Do they have lasagna? No?
I don't think.
There's usually at least one kid in the freshman class who works at Perkins as a dishwasher or something. So, all right.
I used to work there.
Oh, you did? I said there's always one. Last semester it was Little Anglin.
Haven and
Tommy. There we go. And Haven, yep. There's always one. Which is kind of suspicious when you think about it. That just means that Perkins likes to hire little kids and exploit them. But, no. So these two, they're going to say, go ahead and graph these. Tell me what the solution is. And it says it right there in the title. Sometimes it isn't a normal solution. I'll do B because it's nice and easy. This equation. Start at 2. Slope is 2. Up 2, right 1. Or down 2, left 1. I'm going to do them both. Down 2, left 1, down 2, left 1. I connect the dots. There's purple equation. I go to green equation. I start at -1. Slope is 2 again. Up 2, right 1, up 2, right 1, up 2, right 1, or down 2, left 1, down 2, left 1. Now you probably saw it right away at the get-go. They have the same slope. We just did that in chapter 5. If they have the same slope, they're parallel. If they're parallel, there's no solution. Now, it does say use a graph, so you still got to graph them, even if you recognize that before you start. But because these will never cross, they're always that distance apart, then I just say no solution. This one Do you remember graphing by intercepts? We did it with standard form. Remember the whole like cover this one up, cover that one up? Put a 0 in for x, put a 0 in for y? If I put a 0 in for x, I get 2y equals 2. Divide, I get a y-intercept of 1. If I put a 0 in for y, negative x equals 2. I got an x-intercept of negative 2. Okay? So I see those, yeah, they are perpendicular. I see that slope. No, they're not. Wait for it. I got 2 points. Can you see the slope between the 2 points? Up 1, right 2. Ah, sneaky, sneaky. So I can use that to make some more points. Up 1, right 2, up 1, right 2, up 1, right 2, or down 1, left 2. That's graphing by intercepts. If you don't like graphing by intercepts, could you get y by itself? Yeah. 2y minus x is 2. I will add x. Divide everything by 2, everything. So this by 2 is now 1/2 x. This by 2 is 1. And I say, whoa, wait a second. I go to graph this one, and it turns out to be 1/2 x plus 1. I go to graph this one, and it turns out to be 1/2 x plus 1. They're the same line. What did we call that? Infinitely many solutions. Okay. Officially, I'm supposed to say infinitely many solutions. But you know mathematicians, we like abbreviations, we like symbols, so I'm going to say infinite solutions. Okay? Good enough. Do not say all real numbers, because this is not a solution. That's when any number works in an equation. Remember that was, say I had like 5x plus 2 equals 10x plus 10. Well, when I distribute, oh wait, boy, it's been a long week. When I distribute, I end up with 5x plus 10 equals 5x plus 10. 0 equals 0, 5 equals 5, 10 equals 10. I end up with number equals itself. Now it's all real numbers, because any number I can think of, if I put it in there, it's going to be true, because it's called an identity. All right, let's also put on here our big kid words. What is the solution of each system? There are infinite solutions. Do you remember what this one was called, about the whole consistent, inconsistent, dependent, independent thing? Does it have a solution? Yeah, it's got a bunch of them. So I know it is consistent. Does it have one solution or too many of them? Too many of them, so it is dependent. It has no solutions, so I call it inconsistent. Okay? So infinite solutions, consistent and dependent. No solution, inconsistent. You say, I knew you would do the easy one. That's because we did both of them, because there's two different examples of things to talk about. Now you're going to do two of them. And I bet you one's going to be the same line, the other is going to be parallel lines. Just so you see an example of both. So if you can graph by intercept, if you can change it so y equals mx plus b, However you graph best. Go ahead and graph them. Okay. If we don't know how to graph, this is just a big old mess. Y'all know math scaffolds. If you can't do chapter 2, you can't do chapter 3. If you didn't do chapter 5, well, chapter 6 is going to be rough. All these little notes and tips and tricks we're writing down. All of your quizzes are open notes. Write some of that stuff down. Got a couple kids in my Maroon 3 that got a little stack of note cards. Like, this is the holy grail of math. These are the things that he said, for crap's sake, please write them down. They just keep them on a little stack of note cards and they kind of array them around themselves for a test. Those are also the only kids with A's in that class. Use those resources. All right. Y-intercept of -3 is slope of -1. Right? -1 in front of the x turned into a fraction tells me down and right. Make as many points as you can because I bet one of them's the answer. Equation 2, I start at 5, 1, 2, 3, 4, 5. It also has a slope of -1, down and right. So I say, well, wait a second. Those two, oh, forgot my arrows. Not only did they never cross, I see that they have the same slope. So what's the answer? There is none, right? No solution. For contestant 2, if I go and try to get y by itself here, by dividing all of them by 3, I see that these two are the exact same equation. So I'll just graph that equation, start at -3, positive, so up 3, right 1. Little bit off-road. I graph it. Maybe you want to get fancy and like try to double line it so that you know that it was the same line twice. But goes forever in both directions. It's the same line, so I say there's infinitely many solutions. Okay. Now, how many of us have we been going through these, if you've actually been trying them? We're running across problems with our lines, okay? We're going the wrong direction, maybe goofing up whether it's a positive slope or a negative. Goofing whether do I start at this point or that point. If that's a issue, that means you need to get practice. Come work with me, ask questions. Okay? I am more than available. Before school, I'm here every day about 7:30. After school, I usually don't leave until 5. Lunch, I'm just in here hanging out with my nerds. My room's open. My prep's white 3, if you got some spare time. Spartan time, if I'm not working directly with a student, well, belly up to the table. Let's get her done. So, I would like for you to do which one? Oh, 3 of a kind. Cool. All right. Let's do number 4. We got time. Let's do number 4. Just to be safe. Let's do number 4. Make sure we can graph lines. Hey, y'all doing your work and you're not sure if you're doing it right. Say you finally decide to do your homework assignment 8:30 Sunday night. Oh, wait, that's right. Or I suppose because I'll see you on Tuesday night. Or Monday night. Well, if you finally start this 9 o'clock Monday night, you're not sure how to do number whatever, take a picture of the problem and your work, send it to me. Phone a friend. Okay? You got a tutor in a pocket. Just staring at it or waiting for me to write it down will not make it better. You have to try. You got to ask a question. Now, they design these problems so that most, if not all, of the graphs you are encountering, they should be one of these 3 kinds, where it hits in a nice spot, or they're parallel, or they're the same line. If they're crossing out in the middle of a box, and it looks kind of funky, and you don't know if that's 1/2 or 2/3, that means you probably goofed up. Don't just see that there's a 2 next to both of the x's and assume parallel lines. We spent all of first semester working on these equations so that you would remember stuff like that negative is still there. I have to divide everything by -1. I have to divide by the -1 because it's still there. Math scaffolds. Did we remember that from first semester? Contestant 1, I start at 6. 1, 2, 3, 4, 5, 6. Slope of -2. Down 2, right 1, down 2, right 1, down 2, right 1, down 2, right 1. Connect dots. Contestant 2, I start at positive 2, slope is positive 2, up 2, right 1. Up 2, right 1, or down 2, left 1. Connect dots. It's not enough to just graph them and quit. What is the solution? What is the answer? Okay. 1, 1, 2, 3, 4. 1, 4 is my solution. And check your answer. Make sure it actually works. If you just said that 1, 4 is a solution, I should be able to say 2 times this plus this is 6. I should be able to say 2 times this minus that is negative 2. I better be able to put 1, 4 in there and it actually work. 2 times 1 is 2, 2 plus 4 is 6, 6 equals 6, yay. 2 times 1 is 2, 2 minus 4 is negative 2 equals negative 2. It works. I win. Okay. Got to graph it. Got to tell me what the solution is. Got to plug that coordinate back into both equations and make sure that actually works. Anyone tell me why I put that coordinate into the original equation and not into the ones that I rearranged? Why might I want to check my answer with the original problem instead of the ones that I rearranged? I could have screwed up. It has to work in the original because what if I screwed up when I made those and then my check looks like it's right, but it really ain't right because I screwed up. Okay? Always check in the original. Y'all, it's Friday. You're not back in here until Tuesday. You have 94 and a half hours. That's plenty of time to get an assignment done. That's plenty of time to make up work that you're missing. Be aware, like I said, Tuesday, Wednesday next week, we don't know what's coming. We just know it's coming. Oh, and if y'all ever feel like you're broke when that does come, and tell everyone, I used to make a killing by staying in town at my grandparents' house every time we knew we were going to have a snow day. Grab a shovel, walk around, and knock on people's doors. I'd take down $400 a day easy shoveling driveways. Okay? Because old people or middle-aged people with bad backs will happily pay you $50 to go shovel the driveway out. Happily.